All right, so not enough time to complete all. And I would say this paper compared to your electromagnetic field is much easier. All right, hope that many of you can score good result to help a little bit, okay, to improve your CGPA. No senior in class meaning easy. Yes, but there are people who cannot make it in the year 1, SEM 1, so cannot meet the prerequisite, so cannot attend this class also lah. Okay, not your batch, okay, other batches. Hey, your batch also got one, isn't it? What is his name already? I think there's one boy, right? Godwin told me the other day. Jin Yang. Is Jin Yang still here? Jin Yang still attending most of the classes with you? In other classes lah, because I think he haven't attend my analog also. That means that he either haven't passed basic plus the analog electronics or both. But I remember Mr. Tan told me, okay, last semester he sit for basic electronics. But I didn't ask whether he passed or failed lah. Okay, so he definitely cannot graduate on time together with you already. Because he haven't attended, okay, digital logic design yet. So he has to pass that one, then only can join this class. Okay, is this Zian going to attend our class today? Got to remind him. Calling him already. Okay, Song Jian, thank you. Now, have you started your assignment also? This Thursday, we are going to do online, okay, assignment. So if you got any question, you any question related to your programs, okay, you can ask. You only done question 1. Try to do more, okay. Share out the work, okay. They are all in 5 or 6, 5 questions, okay. But one is very easy segment. Basically, that questions, okay. Basically, it's just copy, but take away the clock. Other than that, okay, the rest are the same. So you have to do all the 4, then only can do the last question. Combine them using structural model. I think Wai is the most hardworking boy, is it, this semester? Okay, never mind. So I'm not going to no. Oh, very humble. Well, generally I would say, okay, most of the students in this class here are hardworking lah. Okay, most not all I don't want to mention who are the one who is not hardworking. Wen Jian, anything to say? You want to declare yourself as a hardworking or not hardworking? All right. Okay. Not going to wait for Zian already. I think, okay, we are going to start off with our lecture here. Let me share screen. Okay. Okay. We are going to start off with this comparator here. Of course, when you see the name comparator, you know that, okay, you are trying to compare 2 things together. At least two things. So this is digital. Therefore, you are going to find that, okay, we are going to compare the number, okay, the digit. So a simple comparator, okay, contains this one here. Of course, okay, when we design comparator, our aim here is we just design one, then we can cascade them together. So you are going to find that, okay, I have a previous input. This is the previous input. Okay. So this is the current input. So we are comparing this, okay, with the previous result, okay, coming in as well. Then, okay, conclusion comes out. Should it be G stand for greater, E stand for equal, L stand for less? Now, if previous also, okay, you may also come out with a conclusion, okay, G is less. Before compare this bit, so your conclusion is G is less, or they are equal. Sorry, G is a greater. Okay, previous bit G is greater. Okay, previous conclusion greater. Previous conclusion they are equal, or previous conclusion they are less. At any one time, these three inputs here, only one of them, only one of them here is a 1. Okay, because you only can meet one of the one of the conditions. Okay, either this one, or this one. All right. So based on this concept here, let's say, okay, if I were to build up the truth table, you're going to find that this 1, 2, 3, 4, 5. All these one here are my input. These are my input. This forms my output. All right. So my truth table for this one big comparator, okay, a lot. And you are going to find that, okay, there are some dash over here. Dash here means that this type of condition will never occur. Of course, in this case here, okay, started off with the previous bit, all are 0. Okay, they are input for conditions of greater, equal, and less. Here, all are 0. It is impossible. All right. Of course, you can start off with this, but you know that, okay, if result come out, okay, these three are 0, it is impossible. Therefore, in this case here, the result, okay, that we put for the next stage here, we take it as dash. In this case here, don't care. My don't care. All right. So when I'm comparing this, okay, let's say my L, okay, less. Less in this case here refer to my A less than B. Okay. This one, A greater than B greater. All right. So this is the less equal, of course, A same as B. So if previous condition comes in is less, and now both A and B are 0, so eventually after going through this comparator, you are going to find that output is still maintained as less. Okay, A still less than B. So this one here you can see as just now is less, right? So less, A is a 0. So this is my A, B is a 1. Now both 0, 0 comes in for the case of my A and B. Of course, you compare 0, 0 with 0, 1. A is less than B, right? Therefore, this is the condition that you are going to see. If it's equal previously, now they are still the same. So result come out, of course, remain as equal. Just now, both 1, 1 or both 0, 0. Okay, now still, okay, they are the same, 0. So equal. Not possible to have 2, 1 coming in at the same time. So result coming in, output here, don't care. This condition will never happen. So anything will never happen, you don't care. All right. Okay, this is a greater. Just now, my A is greater than B, and the new signal coming in is a 0, 0. So it's the same as saying that my A just now, for example, is 0, 1. Okay, B, okay, are 0, so 0, 0. First bit, we conclude that my A is greater than B, right? So greater. Then next, I compare the second bit. Result still come out is my A greater than B. And this part here, more than 1, 1. So don't care, don't care, don't care. 0, 0 also don't care, don't care. This thing will never happen. So don't bother. All right. So same thing. We are going to compare this. Now my input here varies. So my B now become 1. A is a 0. So with that, we compare. B, in this case here, conclusion, don't care what is just now, what coming in. Okay, less. Just now you say A is less than B, right? So with this one here, still less than. My A is still less than. Why? Because just now equal. Now with this condition, my B already greater. Just now equal means that could be like that. Now my B is a 1, A is a 0. Of course, you see, okay, B is greater than A, or A is less than B. All right. Although just now, okay, A is a 1, B is a 0. But now if A is a 0, B is a 1 in the next, okay, more significant bit, conclusion that you are going to have here is still A less than B. So in this case here, my A always less than B. Whereas in this part, your A is a 1, B is a 0. You find that, okay, my conclusion, okay, for the result here is always A greater than B. Okay, A greater than B. Only when these two here, they are equal in the sense of 0, 0, 0, 0, or 1, 1, then you find that possibility of less, equal, or greater happens, as I already mentioned just now. Okay, so with this truth table here, now we wanted to find out, okay, what is the conclusions of our this truth table here. All right, so how does the expressions, okay, for greater, equal, or less here will happen? Okay, so based on these parts here, let me just pull out this blank table here. Now, based on this truth table, remember we already learned, okay, 5 input variables. All right, so now we practice again. These are 5 input variables here. So I will start off with, okay, considering my less. So you are going to find that, okay, I have 5 input variables. Actually, suka hati saya lah. All right, what combinations I'm going to put here, what combination I'm going to put here as to make them as one pair. So I choose, okay, A and B as no, over here, like I say suka hati. Okay, I choose this one, I choose the last subsequent. Then this one here, I take Li equals to 0. This one here, I take Li equals to 1. All right, so with these conditions here, you are going to find that my main terms are, so it's a 0, okay, 1, 2, 3, 4, 5, 6, 7, and so on. All right, so we are going to fill up this. And of course, at the same time, you think that, okay, you want to do the one for the E also can, okay? Let's say I do the E at the same time, because I can only see 2. So I do 2 at the same time. So this is EI when equals to 1. Of course, okay, if you do it at the same time, the selections of the combinations here, please, okay, make it the same. Otherwise, you're going to make mistake. Okay, so a reminder, okay, when you prepare your car, no matter the time, please, okay, 0, 0, 0, 1. This is 1, 1. Okay, remember 1, 1, then only 1, 0. All right, students always make these mistakes here. Okay, so in my case here, first one is a 0. Sorry, this Li is a 0 the time. You find that don't care for all these terms here. Like I say over here, I only look at these 2. Okay, so maybe this one later on you all can try out on your own. All right, so first, okay, 0. So don't care. I put it here. So this is a 0. Then followed by second one. These locations are, so you are going to have here, this is a 1, this is the 0. Wait. Do I make a mistake? Let me check. This is a Li. Yes. Okay, so this is the 1 here, 0, 1. Okay, 0, 1, then this is don't care 0. Next, to proceed, okay, you find that this is the 0, a bit difficult for me to see. Okay, then this is the same locations. I'm going to fill in here, 1, followed by 4, is a don't care, don't care. 1, 2, 3, 4. I've done until here. All right. Next, I proceed. Remember, it is here, 0. And this is also a 0. Proceed. This is a don't care. This is a don't care. Do I make a mistake? 101, sorry, don't care is here. I think do 2 at the same time is a bit okay. A bit confusing. Okay, let us just concentrate on 1 first. All right, I concentrate on this E first. E first. Okay, E first. This E first. Okay, so let me just confirm again. Don't care, 0, 1, don't care, 1, don't care, yes, 0, don't care. Then this is a don't care, don't care. So I have done until here already. Okay, next. You are going to find that don't care, 0, 0, don't care, 0, don't care. Then I see don't care over here. All right, so I need to see this one here, E. Then you find that, okay, after doing this, okay, please move to these locations here because, okay, A is a 1, B is a 0, okay, based on these combinations here. And same thing, same location now, don't care, 0, 0, 0, don't care. Then next, 0, don't care, don't care, don't care. I have done until this part. Okay, until this part. Then proceed. You'll find that I have a don't care, 0, 1, don't care, 0, don't care, and this is don't care, don't care. Okay, since I fill in my E already, then now, okay, we try to do looping on this E here. Okay, for the case of E, so this is how I fill in my E. I think I make a little bit of mistake here, okay, the way I write. Still Monday blue. So this part here. Okay. I make a little bit of mistake here. All right. So this is for the case of this one. Whole thing here, this is for E. This is for the L. Okay, for the L. So, okay, we get the equation for the E from here. So you find that when I do this looping for the case of E that time, okay, I got to be very careful, okay? I need to analyze both, okay? So first one I look at is here. I saw a 1 here. So what I do is I loop these 2. Don't just loop these 2 alone. So you find that this 2 is also adjacent. Okay, so my E, so I'm looking for the E, okay, equal, because I fill in based on this one. You can write it as E or E plus 1, no problems. All right, so we know this is for the equal output. Our expressions here is always the output. So my E, just now, if I just write as E, you should know that it refers to my E output, the equal output. So this part here, okay, if I do these loops here, both L here will be cancelled. Okay, you can forget about this L here because they keep on change from 0 to 1. Then what I need to do is I look at it vertically only. So you find that is A, I, B, I. Okay, A, I, B, I. And this one here is E, I. Okay, why I do it this way? So you find that when I do this looping here, because it's the same positions, so you find that, okay, with this part here, with these parts here, Okay. Your just now is AI, BI, both are 0. Now it's AI, BI, EI. Okay, so second loop, this one. First loop that is here, this one. So this is an expression that I obtained compared to here. All right, you find that, okay, this is the result that I'm seeing. All right, exactly the same. Of course, okay, to say, okay, finally your E, okay, or the equal, you want to get an equal output, you must make sure all the way, okay, they are equal. Okay, either both of them are 0, 0, or both of them are 1, 1 at the same time, and all the way they are equal. Cannot be at one time, okay, they are at greater or less. Okay, this is the E. Okay, then we look for the one more time for the L. Okay, the less. Okay, I already done some. I just double check whether I made any mistakes here. So 0, 1. Don't care. 1, 0. Don't care. 0. Don't care. Then this one here is a don't care. Don't care. Okay, followed by don't care. 1, 1. Don't care. 1. Then this is don't care. Don't care. Next. Okay, give you all a hint. Test got 5 input variable one. Okay, Kano map for 5 input variables. So you all must know how to fill in and how to do the looping. So here is don't care. 0, 0, don't care. Next. 0, don't care. Don't care. Don't care. Followed by don't care. 1, 0, don't care. There are a lot of don't care in this case. So 0, all don't care now. Okay, this is what I obtained for the case of L. Okay, less, the less. Okay, so in this case here, we do looping also be careful. We have to look at both. So I have 2, 1 over here, the don't care. All right, I need to consider this don't care as well. So it will be easy for me to look it this way plus this way. Okay, so my less I write here, my less. Okay, less in this case here, with this one here, L, you can forget about it. So you're going to find that, okay, B, okay, as long as my B is a 1. All right, as long as my B is a 1, A is a 0, then you can always say that A is less than B. Okay, no need to care what is the previous condition, that is whether they are greater, less, or equal. So this is one of them. Next, we look at maybe the looping now. We look at, okay, here no more 1, then we focus on this. So you see, okay, 2 more 1 here. Unfortunately, okay, you cannot loop 12, so therefore we do this looping. Okay, we loop this, and with this looping here, you find that, okay, now it's less. Okay, L is a 1, and this part, because all loop together already, so you can forget about it. Just see this. Okay, you find that, okay, A is a 0. Okay, A is a 0, and just now A is less than B. A is a 0. Just now is something like that. Okay, new A is a 0. Just now A is less than B. A is less than B, so B is a 1. A is a 0. Now, actually, no need to know what is the B condition. Then conclusion, you are going to say that my A is definitely less than my B. All right. So this is the explanation. Then proceed with one more. Okay, take this one. So you find that I look it this way, but very blur. So cannot see. All right. So you find that, okay, I look it this way. with this looping here, you are going to find that, okay, now my A, okay, eliminate, B is a 1, okay, B is a 1 with L just now less. So of course, when B is a 1, you know lah, okay, definitely my A will be less than B already, because just now already less. Now B is a 1, okay? Don't care what is the value of A, B definitely less than. So this is the expressions that I obtain, okay, for my less, okay? Now, this one, okay? This one. So the only thing I never show for you is G. So you can try. This is the solution that you are going to have. All right. So you can try on your own. Otherwise, it's very boring, isn't it? Okay. So of course, okay. This is what I obtained from my Kanomat. Is the most simplified. But from truth table, actually, I also, okay, get all this, okay? From truth table, so you find that I just group those 1 under the G category. Under the G, okay, write down all the 1, okay? 1, 2, 3, 4, 5, and then, okay, E and my, okay? The G are 1, 2, 3, 4, 5. And you find that, okay, this one here, with the L, E, and G, that means any conditions. So if this is the case here, any condition, actually you can forget about it. No need this condition. As long as my A greater than B, then I can say that, okay, this with this most significant A now greater than B, conclusion is my A greater than B. All right, so this is a simplified, of course, okay, never go through this Kanomat. I want to go through this Kanomat here. It's just more like a revision so that you remember your 5 input variables of how to do looping in your Kanomat. All right, so we got from this truth table, we got this result and can be further simplified and confirmed using your Kanomat that it is correct. Okay, after getting this result here, of course, okay, we are going to do the design, the internal part of it. So you find that internally, okay, I design, okay, will be based on these equations. All right, based on these equations. So arrange them nicely. Okay, this is my input. So when we draw, okay, we normally draw here as the input. Okay, and I generate our A and B. Okay, A and B, the current digit that we are going to compare. Okay, so based on these equations okay, over here I can only see the L. Okay, this L look like I. Okay, L, then you find that, okay, I just go accordingly, design accordingly, and this is my L plus Li plus 1, the output. Okay, so this one big comparator network here, of course, we can also cascade them, all right, to form many bits. All right, so easy design here is because, okay, you find that your G, E, and L here cannot start off with 0, all are 0. So what you do is initially you start off with 1. Okay, when you haven't start comparing, you say that they are start from equal. Okay, so this is the one that we need to pay attention to. We start off with, okay, they are equal. Then subsequently, okay, we can just cascade them to compare 2-bit, 3-bit, 4-bit, and so on. Remember, there is a propagation delay. Okay, I can only get my final result here after certain nanoseconds later, depending on how much time is being required, okay, for this comparator here to function. Okay, this is the easier design. Of course, if you use VHDL, it's like easy, isn't it? You just compare, result come out. But this is hardware compare lah, That one is using software. All right, that ends this topic on adder comparator, okay, topic. Okay, adder we have done. So this is on the comparator topics. So any questions? Let me stop first. Okay, I was looking just now, look at this one here. I didn't, you asked me, okay, EI 2 times. What do you mean by EI 2 times? Let us clear this part first before we continue. Oh, my connection got mistake, is it? His connection, Adin's connection. This connection got mistake, is it? But anyway, okay, don't remember the connections. Remember how to get equation. Okay, how to get. Oh, okay. Oh, all right. Okay, so don't remember these connections. Okay, please. Okay, remember only equations. This is to show you. Okay, when you want to do any circuit connection, please show it in a very neat and tidy way. Okay, you can arrange it as in this form. You see, I never tell you which one connect to which one. All right, so we don't remember all this. Okay, so is there any questions related that you all want to make it clear first? You're going to find that these topics here covers a lot. Not really a lot, okay, but you can say like trying to recall those devices that you have learned in your year one, and mainly is on the applications, and you see those applications in your tutorial. So once I finish this decoder plus the encoder, then you find out we'll spend a lot of times on tutorial. Okay, depending on whether you know how to apply them, make use of them. Okay, is there any question for today's this part currently? If no, then I'm going to proceed. I think today I can finish my encoder. Okay, now no question. I assume no question. Then we are going to proceed here. Second part. Okay, let me, I'm still sharing. Okay, we look at decoder. So try to recall what is a decoder here. So you find that decoder here having multiple input, multiple output. So maybe just recall first. What why do we need to study decoder lah, adder lah, all these things here? This is because decoder, multiplexer, adder, encoder. Okay, all these are like very common, very common components. And with this style of standard common components, you are going to find that it can make our design here more simple. If let's say I want to multiplex my this input signal, when I want to multiplex my input signal, so you find that instead of I go and use a lot of AND/OR gates, start my connections here, very time consuming, and the whole design is very messy. So why not I just make use of one IC multiplexer, for example. I just connect those input to it, then I can get my output easily. Or if I want to do some design, instead of I start off with an AND gate, OR gate, all these design here, why not think of a decoder for the design? If this decoder can help to make my design here more simple, all right, then go for decoder. More simple, you are going to have a less mistake, and then if you want to do troubleshooting, in case the output result is not what you think is not correct, you want to go and sort out the problem, we call it troubleshooting. So in this case here, decoders helps you, because the only one IC, I just need to test the IC, is it the IC functioning well? If yes, then could be it's a connection problem. So troubleshooting is very easy lah. All right, this is the reason why we need to study all these type of devices. Those are standard devices, and we will combine them later. All right, so you're going to find that decoder here is a multiple input, multiple output logic network. Of course, we have some common one. Common one here is if your input is an n number, then the output is 2n number. Let's say this is a 3-bit. Then you find here is 8-bit, 2 to the power of 3. 4-bit, 16, 2 to the power of 4. All right, so this is the common one. All right, common purpose. Of course, there are some standard, purpose of decoder, like what you see your segment. The segment in the VHDL here actually is my do you all see my screen now? If you cannot see the screen, tell me, okay? Sometimes I don't notice the on this chatbot. So anyway, okay, this is a part here, common one. You find that, okay, the output clearly decided by the input 2 to the power of n. All right, that one is the common one. So there are some special one, okay, like what you see in the lab, okay, our segment is actually also a type of decoder, special purpose decoder. So usually, okay, you will see this lah. All right, the numbers here, okay, depends on the line that you are having here. Okay, so on top of this, okay, we might have, okay, enable input. All right, one enable input pin, 2 or 3, okay, because it depends on, okay, how you are going to cascade them. So can have more than one enable pin, which is not shown over here. All right, now there are these decoder here, okay, which having special functions. And usually, okay, those are specific decoders here, their output is less than the number of 2 to the power of n of input. Let's say input 4 for our segment, okay? The very easy example that I'm going to use, 7 segment, the 7 segment display unit. My input is 4, but my output only 7. Okay? Input is 4, output only 7. Then you may say that, okay, can I use 3 input because my output is 7 ma. Yes, you can, but then, okay, this input here is from BCD, right? BCD need to show from 0 to 9. To show 9, I need 4 bit. Okay, to show 9, I need a 4 bit. So this is the reason why you have 4 input. All right, instead of using 3 inputs. All right, because your input is BCD. My output, I need only 7, for example. Of course, you can have more, maybe add 1 more point for your decimal point. So output is 8. So depends on your design. So this is function specific decoder. We'll look at it, okay, afterwards. Now, another type of decoder here, 4 input, 10 output. So 4 input. 4 inputs here, you find that I want the output, okay, only 10. So output will show me from 0 to 9. Only one of them, okay, will light up. But this one here in binary, okay, also show me 0 to 9, but it's in the form of 4, 0, if referring to a 0 in decimal, or 4001, okay, for the case of 9 in decimal. But here they show you the output is either one of them will light up lah. All right, so this is a type of a decoder. So we call it as binary to decimal decoder. Binary to decimal. Only one of them will light up, or special. The output will be special, only one of them. And these are special output here actually refer to the input combinations. All right, this one here, the 7 segment display decoder, which I mentioned just now. You want to light up the 7 segment. You go and make the output here 1 or 0 according to whichever segment you want to light up. All right. So we also have this enable pin and so on. So you are going to find that, okay, the general one, okay, will be used, okay, for our logic design. So to replace, okay, those are very complex, okay, connections of your AND OR gates, we can make use of a decoder. Okay, truth table first. 3 inputs, okay, general, this is a general, okay, general. So I have 3 inputs. I'm going to have 8 outputs. And look at the outputs here. The output here actually, okay, decode the input. If input in decimal is a 0, ZO will show you a special 1. Okay, the rest all 0. When input is a 1, now is a Z1's turn to show you a 1. So this one shows that my combinations of the input is a 1. The rest are all 0. Let's say this is the one, 5. So I expect Z5 is the special one. The rest are all 0. And this one here move diagonally. Okay, diagonally. So with this, okay, you remember it as output decode the input. Okay, only one output is special compared to the rest. And since this output here is a 1, we say the output is active high or active high output. Okay, active high output. Active high output, okay, if you see at the output there, okay, nothing, just like that lah, So, I mean, got output coming out in terms of their block diagram, okay, active high or like that. So, if it's active low output, so you are going to see bubble, okay. So, if you see, okay, the output looks something like this, okay, every time this one here refer to active low or active low. Sometimes input also can be active low. All right. So as long as you see the bubble, okay, you know that it is active low. All right. So remember the truth table. So based on this truth table here, you find that, okay, you can figure out how does the internal architecture of a decoder looks like. So maybe, okay, based on this table, we just come out 1 or 2. So, okay, do the last one here. So how to get my Z7 is a 1? Okay, Z7 is a 1, so easy. So you just see here, I must make sure my X2 is a 1, X1 is a 1, X0 is a 1. One more. Z7, sorry, 7. This one, Z6. How to make Z6 becomes a 1? Only this combination, that is a X2, X1, X0. Okay, is a 0 in this case. So you have all the very unique equations for all these outputs here. So we form our output based on the equations. So we don't go and remember this as a circuit. So you find that, okay, for the case of ZO, must be 0, 0. Okay, my drawing is a bit bad here. And this is what we call it as, remember, min term 0. This case here, min term 4, if I'm talking about Z4. So you find that is 1, 0, 0. Min term 4. And here I just dot. All right. And last one, min term 7. When input is min term 7, then you find that Z7 will be triggered. Okay. They will give you the unique outputs. This is for active high. Okay. Active high outputs. All right. So remember the truth table, then you will be able to come out, okay, with the internal circuit. And notice here is no bubble. All right. And their output here actually, okay, same as your minterm. That is to say that my decoder here, the output they are generating here are actually, they generate the minterms for me.
Okay, remember this, they generate the minterms for me. That makes, okay, my this combinational design. Okay, if I need those minterm, I can just take from decoder. Okay, take from decoder. All right, so now because, okay, my decoder, okay, give me all the minterm output, so I want to do logic design based on decoder. Here says that it is convenient, okay, to be used when several functions of the same variables have to be realized. Let's say, just take example here. I have two functions, f1 and f2. And both functions here, okay, are going to have this type of minterms, okay? So still remember these are summation. So this is the same as minterm 1 plus minterm 2 plus minterm 4 and your 5. All right, right, as in this form, like in a max. All right, so function number 2, same set of input variable. Their minterm here is 1, 5, 7. All right, let's say this is a case here. Of course, okay, I can design, okay, start off with Kano map, simplify, then find the equation and start to build. But in this case here, if I really learn my this decoder, I can actually make use of decoder, okay, for me to do this design. So you're going to find that, okay, my this decoder here, of course, okay, be very careful of these parts. Most significant bits go to your 2, okay, representing of more significant compared to the other 2. So the connection must be correct. All right, x2 go to 2 here. Then this part here, their output, okay, is minterm. Show me M0 up to my M7. Okay, just now says that my function 1, okay, is of this type of minterm all together, because M1 plus M2. So it's all together. So what am I going to do is I make use of one OR gate. This OR gate here, I make it connect to minterm 1, follow this part. I make it connect to minterm 1, followed by minterm 2, minterm 4, all right, minterm 5. All them together. Then I am going to show the output based on these are input expressions already. Okay, my F1. So I generated my F1 function this way. And for the case of F2, I do the same thing. Okay, 1, 5, 7. So I go and connect to 1, connect to 5, connect to 7. Let's say you are using the same IC, okay? Because in one IC, there are more than one gates available. Of course, okay, in this case here, I will use the 4 inputs. Then inside there still got one OR gate. You're definitely not going to look for another, okay, OR gate with 3 inputs. So you use back the same IC, okay? Same IC. So since, okay, that IC got 4 input, right? So what you can do is the extra input, right? You can connect to any one, okay? So conveniently, I just draw it over here. Therefore, okay, you can just join, making use of the same IC that contains 2 OR gate inside, and you can generate your F2. So in this case here, your design, okay, very neat and very tidy, right? So very few wire connections. All right. And in case, okay, my this output don't give me the correct info that I want, I only trace very few wires. Okay. So this one here is using minterms. Okay, so let's say now, another example, I want to realize the following function. Requirement 3 to 8 decoder, and question say that no OR gate, but they have a NOR gate. So use 2 NOR gates for these applications. And this is the equation that they give it to me based on this truth table here. Okay, I summarize. I got these expressions. There are many, okay, minterms, okay, required for this function F1. All right, so 1, 2, 3, 4, 5, 6. This parts here, you find that F1, So there are 6 ones over here, but there are 2 zeros. So if I were to look at this case here, I'm thinking of, okay, so why should I go and implement a circuit that is complex in the sense that, okay, because of many outputs required, which is F1, looking for a 1. So what I can always do, I take the 0. So if you are taking the 0, you find that, okay, you still can go for midterms here, but now you take 2, 7, right? But 2, 7, wait, do I make a mistake? This is F1, 2, 7, yeah, 2, 7, 2, 7, because this 2, 7 here is 0. So therefore you put a bar to it. Because when you just write this one, it is a 1. So once you bar it, it then become, you are taking 0. Okay, you are taking 0 as the output. So they are the same. Okay, they are the same. Same thing happens to this. So here got 1, 2, 3, 4, 5. So why want to okay come out a circuit okay with 5 gates. So maybe okay we can use a lesser one. I also focus on now the lesser one. Oh, why this is a 6? This one here should be a 1. Okay, I meant it last time. Okay, so this is a 0, last 0. So with this, okay, I focus on 0, 5, 7. Okay, 0, 5, 7. So when I write it, okay, 0, 5, 7. Because if I just write it this way, then I'm saying that, okay, this 0, 5, 7 is a 1. But once I add a bar across them, so you find that, okay, I'm referring it as those midterms inside here actually is a 0. Okay, so we are going to convert in this form. Then question now is, just now use OR gate, right? All right, now with this bar here, you already, then you put a NOT gate. You put a NOT gate, then it is the same as our NOR gates now. So you find that, okay, our output of this decoder now, instead of okay using, I didn't draw out maybe I just do it over here. Okay, so that one a bit panjang lebar. So what I do now is, okay, my this decoder, okay, of course, okay, with all the midterm being generated, 1, 2, 3, 4, 5, 6, 7, 8. All right, so this one here, always be careful. You need to label which one go to which. You can write X2 first, okay? As long as X2 is connected to 2, connection must be correct. Then this one you can just label it as a 0, 1, 2, 3, 4, 5, 6, 7, indicating the midterms. So next, for these parts here, I know I need to OR them first, right? Okay, then I put an inverter for this bar here. And this one here forms my F1. And here, I need to connect to 2 and 7. Of course, okay, if the circuit is not too complex, you draw this is no problems. All right, 2 to 7. All right, next. This one, you are going to have your F2. So, okay, 0, 5. Make sure this one, you join them, okay? This is my 0, 5, 7. So I can implement this circuit, okay, with this one here. Lesser connections. Now, instead of connect 1, 2, 3, 4, 5, 6, I connect 2 wires. Here, instead of connect 5 wires, I connect 3 wires. Again, okay, this part here makes the design here more simple. And if you are using less wire connections, indirectly, we are saying that, okay, you save costs. Okay, if you okay design a lot of similar parts, okay, these are similar circuit, you duplicate a lot, then you are saving, okay, these are connections here. All right. So this part here try to tell you what I have told you just now. Now you see, just now here I make it the bar is over here. I can bring it to this side. Or actually what you can do is just now you got a bar here, right? So what we do is we add one bar to here, add one bar to here, added all right, and then also add one more bar to it. So when we are adding two bar on the same side, okay, if this same side here having two bar, actually you can say that, oh, it is the same as no bar. So therefore you got this expression. So this is one way. The other way is just that bring this bar to this side, just like doing max. So same thing happens to this. Okay, so it becomes this form. So with these forms here, we add one more bar to here, one more bar to this, exactly the same. Okay, so what we are actually trying to play around with De Morgan's theorem. Still remember De Morgan's theorem or not? All right, we are playing with De Morgan's theorem. So we can bring it here, bring it there. Then subsequently, you'll find that, double bar of this one, same as this one, same as this. And this is the expressions that I am, or circuit connections that I'm going to have, for my this type of shifting here and there. Okay, I think I already explained this one just now, and more straightforward. Okay, next. The expression given to you, could be in the max term. Look at here, max term, the M, capital letter or uppercase M. Okay, max term. All right, so expression can be in max term, or sometimes this is a max term, this is the min term, things like that. So what does it mean by max term? Okay, how to get max term 0? How it is being represented? You still find that is a x2, x1, x0, but now it's this one representing my max term 0. This one here is a max term 1. So I write all this first. Okay, so you find is this one. All right, now how this are being related to our midterm. So you are going to find that midterm small letter. So if this is the case here, I will write as x2, x1, x0. I can write as this form. Okay, so you are going to find that if I write in this form, actually you're referring to max term. The bar of it is the max term. Okay, confirm. So since this one here, I put a bar, this whole expressions also I need to bar them. Okay, once I bar them, okay, once I bar them, then you find that this part here is this one plus, oh, sorry, this is a little bit of confusion. Wait, let's say I put min term 0 first. Okay, min term 0, I buy first. So you find that this is this one. All right, it's a x2. Remember the De Morgan's theorem? You break this long bar into smaller bar or shorter bar. Then this one originally is a dot, now become plus. So you have x2 bar, x1 bar plus your x0 bar. All right, this is the min term 0 bar. Okay, I know where is my mistake already. Okay, I forget to put a bar over here. Okay, sorry. Okay, my mistake. All right. So if I put a bar over here, then you find that this is a double bar, double bar, double bar, right? So which is the same as my x2 plus x1 plus x0, which This one here is my minterm 0. All right, M0 is given by bar, okay, bar of this. So if you, okay, take the complements of minterm 0, actually you are getting your maxterm 0. Okay, we can try for 1. Okay, for the case of 1, what we have, okay, for minterm 1, well, I must be careful. 2, 1, 0. So minterm 1 is the same as this is bar, this is bar. All right. So I was trying to tell you here, maxterm 1 is the same as minterm 1 bar. Okay, maxterm 1 is the same as minterm 1 bar. So with this, okay, I try to bar this minterm 1, which it looks something like this. Too fast. Okay. I apply the Morgan's theorems to it. Long bar, you chop it into shorter bar. So you break it. Okay, break this one, break this one. Then here become plus. De Morgan's theorem says so. So with this, okay, I have a double bar x2 plus double bar x1 plus, what's wrong with me on my eye? Okay, let me erase this one. So with a x0 bar. So of course, okay, this expression here is the same as x2 plus x1 plus the x0 bar. Okay, plus the x0 bar. So all what I'm doing here, I'm trying to convince you here, minterm 0. Okay, if I bar the minterm 0, I'm going to get my maxterm. All right. Of course, terbalik. If I bar my maxterm, I'm also going to get my minterm. Okay, so you find out, okay, with this, okay, if the function or expression given to me, whether it's in a minterm or maxterm, I can just play around with it. Okay, with this concept in mind. Okay, look at this example here. I have a functions here whereby, okay, make it smaller a bit, whereby, okay, f1 is given by this maxterm expression. Maxterm expression, we also call it product of sum, POS. Okay, this product of sum expressions, another one. And we can actually transform them. Okay, see this one here, same as this one. Why? Because whatever not appear here, you take it, okay, because this is 0 maxterm consider 0, so minterm consider the 1. So we take the 1. This one consider the 1, taking the 1. So whatever not in the 0, of course the output here will be a 1. We don't talk about, don't care in this case. Okay, 0, 1, 2 is not here, so I write here. 3, then 4. 4 is not here, I write it on the minterm expressions here. 6, 7. All right, so same thing. All right, 0, 2, okay, 4, 5. Not appear at a maxterm here, so it will be appearing at your minterm. Because this one consider 0, this one consider 1 output. So that is to say here, whether, okay, I'm talking about this, the expression given to me is in this maxterm, I also can make use of OR gate to implement it because I can always convert it into minterm. Right? So after conversion, this is the circuit that I am having, making use of OR gate. Of course, you can use NAND gate. If you are using NAND gate, then you implement this one, NAND gate. Okay, you implement this one. So I just show, okay, label it 0, 1, 3, 5. Okay, to get your F1. You can also get your F2 from this NOR gate. okay, NOR gates with 1, 3, 6, 7. All right. Now, whether which one to be used in this case here, it depending on whether I'm having OR gate or NOR gate. Because okay, there's no sort of okay saving or simplify in my circuit design because each of them okay also having 4 inputs. This one 4 input, this one also 4 input. So there's no advantage or of saying okay which one is better, but rather than saying that which component am I having. All right, so I design based on the components that I have, okay, convenient. All right, so this is one way. Next, okay, we try to see here is a NOR gate as I mentioned just now. Then you get these parts. All right, so you can check the design now is 0, 1, 0, 1, 3, 5 connections. All right, and this part here, second one, 1, 3, 6, 7. Okay, 1, 3, yeah, 6, 7. Okay, so okay, this one here is based on the logic 1 output or active high output. So then we try to look at okay active low outputs. Okay, active low output decoder. In the active low output decoder, look at the truth table now. It's totally okay inverse as compared to your active high. Now this one here they still decode okay the input So only okay 1 bit output is different compared to the rest. All right, but now okay the output difference here is a 0. They decode this one. Say like this one here happens at Z4. They decode that input is 4. All right, they decode that the input is a 7. So you have only 1 unique output. So with this, okay, of course we can also okay know how the circuit here looks like, and we are trying to go for this part here, max term. Okay, max term. So you find that okay, since this one here decode this, or since okay I can see is this one okay, make it smaller a bit. Try to look for okay 0, 0. Okay, so this is a 0, 0 come from the ZO, which is a 0, because ZO I take 0, so it's a ZO bar. ZO bar here you get is a X2 bar, X1 bar, X0 bar. All right, so this is the Z0. So with this, okay, let's say I do a little bit of conversions. I bring this bar over to this side or add to another bar such that, okay, my ZO got no bar already. Then you find that the expressions look this way. Okay, I apply the Morgan's theorem. Then you find that this is exactly what I'm trying to tell you. This is the max term. Okay, this is the max term. Okay, so now output here show me the max term if this is active low. Okay, active low. And you end them together in this case. Okay, so my output here show me okay max term 0 in this case here up to my max term 7. And look at here, max term 0, max term 1. Okay, this bar here far away, so the bar should be appear here. Okay, this one here, what do they show me? Okay, this is 4, this is 2. They show me max term 6. Okay, these expressions here, max term 6. Okay, and 6. Last one, all the expressions here with the bar across it. So this is the one. Okay, so this is the max term 7. So, all right. So if active low output, the output that they show me, okay, actually is max term. Okay, with this max terms here, symbol, definitely you see with the bubble. Alright, with the bubble, and be careful of when you draw these input connections here. Okay, now I want to sort of interchange max term with min term design. Here they say that any Boolean function is describable either in product of max term, so you have a product of sum. Okay, so you find that you are using you can make use of a NAND gate decoder. And when you are using NAND gate decoder, of course the output here, when you want to combine them together that time, may not be using OR gate anymore, but now using AND gate. Because for the product of sum is like that, let's say, I just take two, three, Let's say this is one of the term, then you have another term that you want to form this product of sum, then it will look something like this. And there's no need for you to do simplifications because they generate all the terms for you already. So this is one sum, another sum, and you AND them together. AND them together is like a times. Therefore, the product of the sum. So this is one sum, two sum. You AND them together to form the product. So it's a product of sum. How to AND them together? Use AND gate. All right, we are going to use AND gate for it. So with this, you find that, now let's say I have this function with a max term, all right. So you expand it, you got this. So this is exactly what I say, you AND them. Okay, you AND them. So with this, I have my this active flow. Okay, active flow output. I AND this active flow output to form my product of sum or max terms, expressions, max term expressions over here. Okay, I just AND them together based on 0, 3, 5, 0, 3, 5. This one, I also AND together 2, 3, 4. All right, so you can play around with all these, De Morgan's theorems. Okay, so I got my expressions here. So now sometimes here is should I convert my expressions here into a min term or should I convert it into max term? Okay, so sometimes here depends on whether you have 1/2 of the total possible max terms occur in a Boolean expressions. Let's say I give you this one. I say min term 0, 1, 5, 6, 7. So you know that for 3 variables, this is more than half already, more than 4. Then if this is the case here, I may want to consider max term. So what is inside here? Not appear here. 2, 3, and 4. So you find that lesser terms compared to this. So this is what does mean by 1/2 of the total possible max term. So then you find that we can always try to replace it, make it more simple. So in this case here, if it's max term, also the same thing here, 0, 1, 5, 6, 7. Then I can convert them into min term 2, 3, 4. So if I was given this part, if I were to be given this one, then I convert it into this form because it's more simple. Then instead of using N, now I'm going to use NAND for this implementation because I try to generate my min terms now. So look at this example here. Purposely, give you more than half, more than 5, more than 4. More than 4. So take this, these are all the process, that they work out. So first they add 1 bar to it. 1 bar to it. Then you find that, so because you are taking 1 bar, so no more considering this expression. This is a 0. Now you try to convert. Try to get the 1. Same thing here. So adding 1 bar again, extra 1 bar to this, extra 1 bar to this. All right, then you are going to find that this part of here actually is the same as the min term 256 already. Okay, same as this. Not haven't show you yet. Then okay, once I have these parts here, then you find that okay, I can use NAND gate to implement the functions. So because over here until here you get your F1, right? Okay, until here you got your F1, which is from this is a F1. You end them together. This one here now 256. Okay, you end them together. You are actually getting F1 bar. All right, and one more time, you're going to get your F1. So I based on these expressions. Okay, F1 bar, you got it from here. Okay, no? So I end, okay, 256. Okay, N256, I'm going to get my F1 bar. But this is not the answer that I want. What I want is F1, so an inverter. After the N and inverter, so you get your NAND gate, okay, to obtain your F1. Okay, next. For the case of F2, same thing. I only consider 0, 7. Okay, so your F1 is of this floating bar. Okay, F1, because here got double bar already, F1 is of this whole thing here bar. So I take 0, 7 and at first then bar it. So get your NAND gate at these outputs over here. So my this NAND gate versions, okay, of NAND N to 2N lines decoder can also be used to realize expressions in min-term canonical form. Okay, these are transferring min-term into max-term or max-term into min-term. These are transformation, so that any decoder given to you, okay, just think about it. Should I use min-term to do design or should I use max-term to do the design? Play around with it. More practice, okay, in the tutorial. Now here, example, I have this one. Both are 4 terms. Okay, both are 4 terms. Okay, so these functions here can also be written as in this form. So this is min term, this is max term. So if it's for this part, let's say, okay, case 1, active high decoder. Active high here, decoder refer to output is active high. Then if you use this one, min term. Okay, min term. So you find that, okay, you are going to use OR gate for, okay, for grouping them together. You OR them together. You OR them together. If you were to be given max term, okay, if you are given max term, so what gate am I going to use? You find that you are going to use NOR gate, active high. If my decoder now is an active low output, if expression given is max term, then I'm going to use AND gate. If expression now is the min term, then you are going to use NAND gate. All right. So maybe, okay, this is for you to understand, or we can make a simple table before we do all this. Okay. So here is the output of decoder. Okay. So we say active high. Another one is active low. So expression coming here is either min term or max term. So if it's min term active high, you use OR gate. Min term active high, you use OR gate. Max term active high, you use NOR gate. Okay, this one active low, max term I use AND gate. Min term I use NAND gate. Okay, for the design. Okay, so based on this, okay, now this expression given to me, you see I can change it to this form or change back to this form. Suka hati, right? So it can be in min term expressions or max term expressions. All right, then now depends on what is my decoder's output? Active high, okay, use all for this one. Active low, okay, then you want me to implement max term, I use NAND. You want me to implement, okay, max term, I use AND. Min term, I use NAND. Things like that. All right, so with this, okay, this part currently, okay, I'm using AND gate. I take AND gate, then is active low. So 1, 3, 4, 5. So you find that here I connect to 1, 3, 4, 5 max term. Okay, this circuit we implement max term. Same circuit, but now I implement min term. I'm using NAND gate. So 0, 2, 6, 7. Okay, that's why I use here all. In this case here, both are equally good because both of them, okay, they are input also 4 bits only. Okay, so normally your decoder will have more one or more, okay, additional inputs. They either call it as an enable input, okay, or slopes. Okay, inputs, depending on, okay, manufacturer, they use the terms. So let's say, for example, okay, we go for very simple here. We want to do expansion, okay. My enable here, I need to have a lot of input variables. Then you find out, okay, 3 to 8 not enough. Maybe 4 to 16 also not enough. Then I want to do expansion. Okay, so we try to make use of this one here for expansions. Now, because we have enable, in this case here, I assume my enable to make it work must be a 1. If it's 0, don't care what is the input condition, all my output are zeros only. Okay, not responding or not working. Only when enable is a 1, then you find that I see a unique 1 here. Okay, and unique output appear at the output pin. Okay, then you find that, okay, of course, this one here, I assume, okay, we know already how to get the output. All right, so the difference compared to previous one is now I add in an enable. All right, you add in the enable, so your these are AND gate here, you find that, okay, more input coming in. Next, okay, you make sure, okay, output you include the enable, active high in this case. Okay, active low. If my enable is a 0, okay, now enable is a 0, you find that E with a bar across it. Okay, E with a bar across it. That's why we don't remember all this. So we look at the symbol, this one here with a bar. So they need a 0 to make it work. When it is a 1, okay, sorry, not working. Okay, this is only one of the combinations. It can be, okay, enable is a 1 and output is a 0. Okay, active low output. Okay, so of course, okay, with this, okay, you are generating max term. Okay, max term. So this is the max term 0 up to your max term 3. Okay, if you see enable is a 0, then you see a bubble in front. All right, sometimes they don't write a bar, but they draw a bubble in front, indicating, okay, in terms of block diagram, they can draw a bubble. But in the truth table, they have to add in the bar for you. Okay, So they're generating the maxterms here with the enable input. Okay. So here they say, okay, the enable input provides the decoder with additional flexibility. Example, if I have a digital network, I want to design which accept data info and must be channeled it to one of 4 outputs. So you can use a decoder as shown. So you find that no problems. But then for expansion, so I don't want to read this. Now for expansion, okay, I have 4 inputs. 4 inputs, okay, x3, x2, x1, x0, and we have an enable, okay, enable. So you find that, okay, with this enable here, this is my first level. First level, I connect, okay, make my most significant as the input. The 2 most significant are x3 go to 1, x2 go to 0. Of course, I make this one here working. My enable, I make it connect to 1. So out of these are 4 here, which one will work? It depends on my output of this first level decoder. Because we know that, okay, you need answer. So if this is a 1, okay, all others will be 0. So if this is a 1, only this one will output some info. Only one of these output here will give you, okay, a special one. All right, they decode. Okay, they decode the number. Okay, and we try to understand what is the number that this one here decoding. Now, x3, x2 are 0. Okay, because this one here 0, then only can choose this one. Okay, this one decode 0, 0. Okay, so when come to here, you find that, okay, I'm taking the second bit. So x1, x0. So this is the input combination that they are decoding, or this output is decoding. And in this case here, all the other 3 decoder not functioning. So you are going to find that their output all are 0 because their enable is 0 in this case here. That makes, okay, this decoder here not working. So all are 0. So what is the input combination? This is the one. Okay, so you can expand your decoder as in this form. So this is just a simple 3 leg, okay, structure. Of course, you can make use of a bigger size decoder. Then instead of 4 variables, you can expand to 5 to 6, okay, 7, things like that. You can decode more things. Okay. All right, that ends this topic on decoder. Any questions? Okay, so a bit too fast to ask your question. Maybe we take a break, okay? 1.5 hours, take a break. Okay, 10 minutes break. So 11:42. I think we can straight away do this tutorial already after this. All right. So one more topic on this encoder. You do it on Thursday. All right. That's why you need to do tutorial. Okay, while you are doing tutorial, actually you are digesting. You see, you start to recall. Okay, why I must do it this way? Why I must do it that way? Things like that. Okay, so see you again. Okay, at 11:45. Then we continue with tutorial. Okay, is there any questions to ask? Anyone did digest a little bit just now? Okay, if no question, then we look at this OneNote. Uh, where is the classroom? Okay, now this is the question we say that we are going to discuss. Okay, haven't discussed and going to discuss today. Kibun is the one who did this question, is it? So let's check at the back here. So all right. So now this is the circuit. Of course, okay, I have to assume that, okay, you have done your this D flip-flops. Okay, already designed the D flip-flops. So now let's check whether is it correct. Now, as I mentioned, okay, I have only one input, clock, 3 outputs. All right, that's all for this circuit here. Where is my draw? Okay, so can use blue. Okay, so clock. Let's check. Entity port clock in standard logic. That standard logic vector 3 down to 0. Yes. Scene state machine looks okay for this part. Architecture structural of this one here name must be the same. Component D flip flop. Not sure is it mistakes here. All right. So in my D flip flop, definitely I'm going to have a D input, clock input, as well as my output. Okay, Q and Q bar. Oh, this is your Q bar, is it? All right, you can do it this way. Okay, so clock in Q bar. Okay, then you never end component. Okay, add in and component. Okay, after this, then only go and get the wire, your signal. So like say, okay, our signal label here, we see, okay, we want to know exactly, okay, where is it? So it's easier to put label it this way. QA, QA bar, QB, QB bar, QC bar, and the logic. Okay. Then begin. Okay, you are calling this one here as DFFA, DFFB, DFFC. So you are using this one, okay, DFF pop map. Based on this one, clock all will be connected to the clock. First pin is clock, all connected to the clock for all the 3 flip-flops. Okay, next. DA, D is the input. This one you connect to DA. This one connect to DB. This one connect to DC, correct? Then the output, okay, you call it as a QA. Okay, so all connect to wire. Yep. All right. So then Z you say is Z is this one. Z is your output, right? I think Z is wrong. All right. Z is wrong, because D is input so it should be QA. Yeah, QA concatenate B concatenate C. Okay, Z is given by this one. Then this part actually don't need, okay, don't need this one because you see they are going to when you got a clock go in, let's say you have a clock go in, this part here clock. So automatically they will go to the D flip-flop to activate, make the D flip-flop working. Make the another D flip-flop, this one, they actually work together lah, because they connected to the same clocks here. So all these flip-flops here will work together the moment you have a clock go in. So you no need to wait, okay? No need to mention about this. You need to describe the circuits only. So now I really okay describe okay the connections for these parts here. I only also show you that okay my Z okay is given by this one here. All right, they are concatenate. Okay, these three concatenate together. Only thing I haven't tell you is okay how to get my DA, DB, and so on. So over here, I need to tell you DA is connected to which connection. All right, so well, if I'm correct, here why you put a semicolon? All right, don't put a semicolon, okay? You describe the circuit QA end with QB bar. So this one end with this one end with this one. Okay, I think something is missing. Okay, okay, end with this one. You all them first. Okay, you all them according to the circuit. Then only this one you put a semicolon. So this is one, okay, one line. Okay, one operations. I have to end first, end first, end first. Why I say end first? Because you put bracket, mah. Okay, I have to end all this first, then I all the result of these end operations. All right, then DB, you end it first. Okay, this one, DC is given as QC bar. All right, so I didn't check the circuit, so I'm checking the way you are right. Then you end the structure. So normally, okay, after this, okay, only we put our Z here. Okay, I'll put our Z over here because okay, things here will change. This part here work sequentially. Okay, one after the other. Okay, my D input here change, go into this D flip-flop because here once here change, go into the D flip-flop, then will cause the D flip-flop to change and cause the Q, the output, okay, a different value at the Q here. Okay, so normally our Z, okay, we put it at the back here. So in terms of syntax, you put it this way, definitely no problems. But it may affect your result if the Q, okay, changing. All right. So syntax, no problem because this is more like a logical error rather than syntax error. Okay. So now better confidence to write structural model. Anyone with any questions? So better now, okay? So you will try, okay, apply this structural model in your assignment, the last questions. Okay, what about the rest? Jane, when Jane start doing your assignment? Belum. So not much time. Today is Monday. Thursday, okay? You're all lazy. Everybody also lazy. Others, okay? Brian, any questions? Brian? Okay, so if no question from you all, can I say that okay, I consider okay tutorial on VHDL all done, and most of you okay, I cannot say everybody okay, most of you okay know what you are doing. Yeah, one more guy I to ask is no Yin Xian, do you do any homework? Yin Xian, Yin Xian go for lunch already. Okay, Kok Wing, I didn't okay Kok Wing eh? Wow, these people okay, where are they? Are they still in the class or not? 8 others should be in. Hmm. Okay, don't want to waste time. Okay. So like I say, okay, I consider I have done VHDL lah. So now we look at this tutorial 2 on combinational. The very first part here is on multiplexer. Okay, let me go and get the questions. Combinational. Yep, this is what I did the other day. Okay, for 5 variables. Of course, okay, complex one. Okay, one tips. Test cover 5 variable. Exam also cover 5 variable. Okay, exam and test both having 5 variable expressions. All right. Therefore, I have no this part here for you to practice. Answer should be the same as what you have on top. Okay, so this part here is using E bar and E. Okay, whereas the top here is using A. Either A or E only. Okay, we don't take okay in the middle one, the B lah or the C here. All right, you are trying to kill yourself only. So please try this one here. Okay, please try this. Okay, so let's now look at question number. Maybe I choose okay some questions to discuss over here. Okay, question number 4. Okay, we look at question number 4. Talking about min term and max term. Question 2, I'm waiting for you to do. So I add page to question number 4. Okay. Okay, question number 4. Answer is here. It's given. Now let's think about it. You are expected to design a combinational circuit that accepts two 2-bit binary number and generate the 4-bit products of the two numbers in binary. So first thing here is before looking at this, what does it mean? Okay, design a combinational circuit that accepts two 2-bit binary numbers and generates the 4 products of the two numbers in binary. Think about it. Okay, what are they talking about? So this one, close it first. I go and get my truth table.
Okay. Anyone with any suggestions? Anyone with any suggestions? What does it mean by here by a design a combinational circuit that accepts two 2-bit binary numbers and generate the 4-bit products of the two numbers in binary? Okay, so of course, first thing here I must know here is that there are how many input and how many outputs in these circuits. So I'm required, okay, to design this one. Okay, they say here accept two 2-bit. This is 2-bit, another 2-bit. So two 2-bit lor. All right, I can call this one here as a A0. This is A1 A0. This is B1 B0. I just label my input as like this lah. All right, so this whole thing here come from A. This whole thing here come from B. So they say generate the 4-bit products. 4-bit products. Okay, 4-bit product. How, okay, am I going to get my product? If I have my A times with my B, then only I can get product, right? Doing max lah now. So the result that you obtain here is product. So these products here got 4 bits. So I expect to see the output here is 4 bits. So since it's product, okay, I may label it as a P product, okay, P3, P2, P1, P0. Okay, so I'm expected to design a component look something like this. Question mark inside my homework for this part. So therefore, I know here I got 4 inputs. Okay, so suka hati, I label this one as B or A. This is what I call suka hati. Up to you. A first or B first. Okay, so if I label it as this case as a standard, keep on changing. Okay, after every 4, okay, by right, I should draw a line lah, but here I use a color to differentiate them. All right, so every 4 we use a line, draw a line, then easy for us to see only. Then you find that, okay, keep on changing. Every 2 bits you change, every 4 bits you change, every 8 bits you change. So 1, 2, 4, 8. And the output in this case here, as what we can see here, P3. Okay, too small for me to write, so I write on top. Okay,